Okay, so I think that they put me second to break up the technical information. This is very, very just site information, practical example of using high volume SCM SCC in mass concrete applications. So I thought that choosing this topic to tie mass concrete in with this is kind of perfect, because what do we know about mass concrete? It generates a lot of heat. And how do we combat this? By replacing some of the cement with an SCM. This is more common in conventional concrete, but my presentation is to highlight scenarios where we would use large replacement of SCM with SCC mixes and how we can benefit from it. I should have put the Ellis Dawn logo on this as well, because a lot of this work was done through Ellis Dawn, my past employer. So I'll start by highlighting the project where we really realized the potential of using high volume SCM mixes, which actually wasn't even with the thought of sustainability in the front of our minds. Then I'm going to explain how SCC got brought into the mix and how it can be beneficial to use in other scenarios as well. We'll look at some data on how these mixes perform in regards to durability, if they're designed properly, highlighting the sustainability benefits, and then touch on the challenges. I say that because they're preconceived, and then the actual challenges still being faced with these mixes. So this is a project where I got a lot of exposure to mass concrete, the Eglinton LRT or Crosslinks project in Toronto, Canada. It's a design and construction consortium comprised of Dragados, To show you the scope of the work of this project, it started in 2015, a lot of tunneling involved, and it's to be completed next year. There's 3 types of stations, 12 underground stations, including the interchange stations. They use a cut and cover method to support excavation. This entails opening a section of space to allow work below grade. They basically just dig down, they put up their tiebacks, and then they put wood planks so that they can work underneath while traffic can still travel above. And then they move on to the other side of the street. This is the main method that they used. This is a photo of it actually happening at one of the stations. The process takes about 14 months to cut and cover. 3 of the stations are mined stations and 1 is partially mined. What they do is they just dig the station entrances and then they install shoring around the sides of the pits and shotcrete, and this allows them to continue working with minimum impact on traffic. This is just an example of the mine station. They line this with shotcrete, and then the station box is constructed. Then there's 4 interchange stations that allow transit riders to connect through to other transit modes. And then there's also 10 surface stops, which are located along the red line on the east side there. And finally, 2 portals that go from underground to above ground with elevated guideways. The purpose of me showing you all of this quickly is to emphasize all of the concrete on this project, and basically all of it is mass concrete. So we went into this project knowing that the majority of the pours were considered mass concrete and had to meet the specifications. As I mentioned, what do we know about mass concrete? It generates a lot of heat. And how do we combat this? By increasing the amount of SCM or supplementary cementitious material in the mixes. For the purpose of this project, we were using SLAG. Here's a timeline of the elements we dealt with over the course of this project. All of which we had to go through the same process for approval of these high volume slag mixes. In 2015 and 2016, we did trials to prove out high volume slag mix, conventional high volume slag mixes. And then in 2017, we realized that there were a lot of congested areas on the top down roof slabs. So we had to redo these trials with self-consolidating mass concrete. And then in 2018, we realized that some of the roof slabs that were already poured, we couldn't get forms in underground. So they actually had to do these trials with high volume slag shotcrete. But for the purpose of this presentation, we're going to focus on the self-consolidating mass concrete. I'm sure you all feel me at least a bit when I say that things always come up last minute in construction. And it wasn't until we were actually constructing some of these top-down stations where we realized that the bottom of the roof slabs were super congested with conduit. So it's basically impossible not to use an SCC mix. So after we spent a full year developing thermal control plans for the conventional concrete mixes, we didn't have as much time to perform the trials, but we managed to do it. This is a very blurry photo showing a cut through of one of the roof slabs where the bottom layer just had a lot of conduits. So we decided to pour the bottom layer with SCC and then top it with conventional concrete and had stay forms so that the SCC wouldn't flow all the way to one end. So to stop that project, let's talk about some other mass concrete applications where we might need to use SCC. Post-tension beams, like the photo on the right, typically large elements that are considered mass concrete and super congested. And then intricate structural elements like the photo on the left, another top-down roof slab that this was constructed actually just before the Eglinton LRT was constructed, where we used a semi-SCC, and we were actually limited to 50% replacement for this and actually had issues, which I'll show you after. And then the V columns that you can see there, we pumped SCC into those, also mass elements. There are large elements that need to use SCC for many reasons, but they also need to use high volume SCM to reduce the heat to avoid cracking. So it's great to talk about using high volume SCM and SCC for whatever reason. You might need it, whether it be for saving money, saving the environment, or for our case, this was just for meeting the specifications of maximum temperature and maximum temperature differentials. But we're still seeing pushback from owners. So first we had to convince the owners and designers that using high volume SCM SCC would be okay. We were dealing with stringent DOT or Ministry of Transport specs, which they basically allowed a maximum of 49.9%. For durability concerns, we've worked through projects with this maximum SCM, like I showed you before, and we exceeded the temperatures and had to fight NCRs for many months. So we had a handful of meetings with the design team to convince them that increasing the amount of slag was the only way to successfully build this project. This is a clause from CSA saying that typical replacement levels fall within 25 to 40%, but there is precedent for using up to 75% slag in industrial and heavy civil construction. And then another table from CSA stating the maximum percentage of slag is 70%. This is just a graph of replacement versus temperature rise, showing that the optimum amount is around that 70% value where we start to see a plateau. And then finally, our own trials for another project we had worked on using this was a 2-meter monolith where we did trials of both 50% and 70% replacement. You can see the benefit of the heat reduction with the 70%, the blue line. The red and green were 50%. The difference was with the placing temperature and the drop in the top. So 70 degrees Celsius is 158 Fahrenheit. So we hadn't fully convinced the designers based on that information, but they allowed us to push forward and continue with our trials of our proposed SCC mixes. The biggest thing that we needed to show them was that the concrete would meet their requirements for maximum temperature and differentials. The hardened properties of the concrete would be within their specified limits for durability purposes, and that this new add-on was that the SCC was stable. So we decided to do all the necessary testing to be able to create a thermal control plan because we knew that would come up as well. So we went above and beyond with the amount of tests that we ended up doing. And in the summer of 2016, we went about the work, doing the upfront work necessary to produce these thermal control plans. And then in 2017, we updated them to account for SCC mixes as well. This involved doing trials, mock-ups, computer modeling, calibrating the models to produce a 266-page document explaining the process to ultimately give the project a bunch of tables like this, where based on the ambient conditions and the size and the insulating value and the concrete temperature, they can get an idea of what the maximum temperature of those elements would be and the temperature differentials. So let's get into the testing of the SCC. We had to test the fresh properties and hardened properties, but then also now moving into the SCC, we wanted to test the rheological properties as well to make sure that the viscosity was not compromised with these high volume slag mixes. Here's some photos of the process making cylinders. We also did some heat simulated curing as well. Prisms for shrinkage, just some fresh property testing at the plant. And then we cast 6 large elements. This is actually for the conventional concrete, just showing that we cast these really, really big elements. And we've learned since then that we can cast 1 by 1 by 1 meter fully insulated cubes. A lot less waste that way. So this is what we did for the mass SCC testing, where we put thermocouple or temperature probes within the elements to monitor the temperatures. And here are the graphs of the temperatures recorded. So this is 70% slag SCC mixes. If we zero in, we were working with 3 different suppliers. If we zero in on one supplier, it's easier to see the results here. The yellow line is the yellow and red line are the core and bottom temperatures. Shows how well the cube was insulated. And then we had a third-party testing lab come and take cores. So that's where you can see the green and purple line are dipping as they open that cube up. But the maximum temperature here was about 63, just over 63 degrees Celsius. So what we did is we modeled it using a software called ConcreteWorks. It's just a quick way to predict what the maximum temperature would be of these mixes. And when we did the model, it actually peaked at 64. So we're very close to what we had measured in the field. And then we took those results and calibrated it to be able to create the table that I showed you. So we just changed the ambient temperatures, concrete placing temperatures to understand what the maximum temperature and differentials would be to give the site team a plan that they can work through the project when using the SCC. So we had proved at this point that using high volume SCM in our SCC mixes would be necessary to lower the maximum temperature. So then let's look at the fresh properties as well. We went through a bunch of phases. This was phase 1, just laboratory trials, where we tested a normal SCC as our control and then started lowering the amount of cement, trying to target a similar workability parameter like slump flow, T50, VSI. We also use shear vanes to understand the yield stress of these mixes. And then we did full batch testing as well. We had set a slump target between 650 and 750. We had 3 suppliers. The second one we had to redo because you can see that in the third column, their viscosity was a little bit too high for what we were looking for this application. So we rejected that load. And then you can see that just with the results of the shear vanes on the far right, we went up to 8,000. So it wasn't workable enough for us. And let's take a look at the hardened properties. The strength specified just for this mass concrete was 35 MPa, so we were well above that. At 28 days, we're 63 MPa. And it was a big concern with using this amount of SCM was the strength gain, which we were able to prove that it wasn't an issue. And then we also performed strain calculations, and we realized that the cracking probability could still be low with a 20-degree differential. But what was interesting is that the strain capacity with these mixes was also higher than a conventional mix, which is a good sign for this to use. Here are the Coulomb ratings, low at 91 days as well. Hardened air void results slightly higher than what we saw with our conventional mixes. Sorry, I didn't put the value there, but still low enough. And also low shrinkage results for all of the three suppliers. So with all that information, we had proven to the design team that increasing the amount of slag allowable to 70% in our mass SCC mixes was a viable option. And it was actually necessary to reduce the heat and comply with the thermal requirements that were given to us. So it was a big hurdle that we had just overcome. It wasn't until a few years later that we actually started looking into the environmental benefits of replacing so much cement on such a large scale project. This article was actually released March 21st. So it was under development for a while. You guys can Google if you want, Renew Canada crosslinks. It gives a lot more information, detailed information about the mixes and the impact on this project. But this kind of puts it into perspective that by using 70% SCM, the project was able to avoid nearly 130,000 tons of CO2 equivalent. Obviously, all mass concrete mixes have some percent of SCM to aid in temperature control, but the impact of increasing the volume of SCM is still significant. For context, the emissions reduction realized here is roughly the same amount as taking 28,000 passenger vehicles off the road for a year. So challenges, the first challenge we came across was that people thought that the concrete wouldn't reach strength early enough, so it's going to delay their schedule. This is my only promotional slide in the presentation, but with mass concrete, it's generating a lot of heat, so it's also gaining strength from that heat. So what we did is we were monitoring all of these mass concrete elements, and we're able to match cure the cylinders for the early age curing. So they're actually getting a lot more heat than what a standard cylinder would get. This is an example of comparing a standard cured cylinder for 2 or 4 days versus what a match cure break would be. And the real challenge, I mentioned it earlier, DOTs, sorry if anyone is here from the DOT, but still trying to push the specifications. This is a current project that Dawn is working on, we're monitoring, but they are only allowing 25% replacement in these massive columns. They're 2 meters by 2.4 meters. You can see how heavily congested they are. So they're using SCC. And as you can see from this data, they're already going above, even though the ambient conditions are so cold, they're going above the specified limit. And that is my presentation.